Until now, we've tackled the problem of learning a model structure or parameters from the case of complete data. We're now going to move to what turns out to be a much harder situation, where we're trying to learn when we have only partially observed data. This arises in a variety of settings. It arises when we have a scenario where some variables are just never observed, they're hidden or latent. It also occurs when some variables are just missing because some measurements weren't taken. It turns out, as we'll see, that these settings provide significant challenges, both in terms of the foundations, defining the learning task in a reasonable way, and from a computational perspective, where, as we'll see, the computational issues that arise in this incomplete data setting are considerably more challenging. I mentioned latent variables. Let's try and argue why we might care about latent variables. So one reason is that latent variables can often give rise to sparser and therefore easier to learn models. So let's imagine that this is my true network, G star, where we have three variables leading into this variable H, and then the three variables at the bottom. And if all variables are binary, then this is a network that can be parameterized with 17 independent parameters. But now let's imagine that I've decided that H is latent, and I'm just going to learn a network over the observable variables, which are the X's and the Y's. And so what is the network that correctly captures the structure of the distribution P over X1, X2, X3, Y1, Y2, and Y3? And it turns out that this network, if you think about it, has first, because H is not there, an edge from every X to every Y. And furthermore, because the Y's are no longer conditionally independent given the X's, because they're only conditionally independent given the H that I don't observe, then I have also edges between the Y's directly. So the spaghetti actually turns out to look like this, with a total of 59 parameters in the network. So by dropping this one latent variable, I've created a model that is much harder to learn. Now, of course, learning a model with the latent variables is by itself a problematic situation, but it may well be worth the trade-off. So the other reason why we might care about learning latent variables is because they might be interesting. They might provide us with an interesting characterization of structure in the data. And I'll give examples of that in a later module. But for the moment, just as a teaser, imagine that we have a data set corresponding to 3D point clouds that are scans of a human body. And we would like to discover from that what is the limb structure of the person to which the scans correspond. That is, we want to identify clusters in the data, clusters in the point clouds that correspond to body parts. And so we want to basically end up with an output where each point has a latent variable representing which body part it belongs to. So having motivated why we might care about missing data, let's think about some of the complexities that arise. So let's imagine that somebody gives us this sequence over here and says, here's these question marks that correspond to missing data. How do we treat this? And the answer is, if you don't know why these data are missing, you have no idea how to proceed. And so to understand that, let's consider two different scenarios. The first one is an experimenter is asked to toss the coin, and occasionally the coin misses the table and drops on the floor, and the experimenter is too tired to go crawl under the table to see what happened, and so they don't record the value of the coin in the cases where it fell on the floor. Case two is the coin is tossed, but the experimenter doesn't like tails. For some reason, tails are give them the heebie-jeebies, and so tails are not reported sometimes. Note in these two cases really should give rise to very different estimation procedures if we're trying to learn from this data set. Specifically, in the first case, we should probably just ignore the question marks and just learn from the sequence of observed instances, HT, HH. Because the other ones, the fact that they're missing, it doesn't tell us anything about the coin. In case 2, on the other hand, we can't really ignore the missing measurements. We need to learn from the sequence H, T, 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 H, T, H, because ignoring the missing values is effectively ignoring something that is predominantly or entirely tails. And so we would get incorrect estimates if we just ignored them. So in order to correctly learn with missing data, we need to actually consider the mechanism by which the data was made to be missing. And so how do we model the notion of missing data? So let's imagine that we have a set of random variables that define our model, and in some instances we may observe some but not others. And so we're going to define a set of observability variables, which are always observed. And basically, O sub I tells us is 1 if xi is observed, and 0 otherwise. And so we always know whether we observe the variable or not, and so OI is always observed. And now we're going to add a new set of random variables, which are also always observed. These are the variables that we're going to call yi, which have the same value as xi. So each yi has the same value space as xi, except that there is also the I didn't get to observe it value. And so in the real data case, in the real scenario, we basically get to observe the y's, and we get to observe the o's, and the x's are not observed. Now, the y's are a deterministic function of the x's and the o's. So yi is equal to xi when o is observed, and is equal to question mark when o is not observed. So in the cases where I have OI is equal to 1, I can reconstruct the value of xi, but for the cases where I don't have the observation, I can't. And so this is a way of just defining the observability pattern that I have. With this set of variables, I can now model the two different scenarios that we had before. In this scenario, which corresponds to the coin falling on the ground every once in a while, we have a separate model over here that represents our observability pattern. And we see that a variable is sometimes observed by chance, and that the target and observed value y depends on x and on o, but there is no interaction between the value of the coin and whether I end up observing it or not. By comparison, in the case where the experimenter doesn't like tails, we see that the true value of the x variable affects whether it's observed or not, and so we have an edge from x to o. So in which of those cases can we ignore the missing data mechanism and focus only on the likelihood of the stuff that I get to observe? And the answer is, one can define a notion called missing at random. Missing at random is a way for me to say I can ignore the mechanism for the observability and focus only on this piece over here. Or, well, say that, the observed piece. So one can show that it suffices for this question, for focusing only on the likelihood, that this distribution over x and y and o have the following characteristics: that the observation variables O are independent of the unobserved x's, which we're going to denote h, given the observed values y, which are my data instances. Which means that if you tell me the values that you observed, then the fact that something may or may not have been observed doesn't carry any additional information. Now, this is a little bit of a tricky notion, so let's try and give an example. Imagine that a patient comes into the doctor's office, and the doctor chooses what set of tests to perform. For example, the doctor chooses to perform or not perform, say, a chest X-ray. The fact that the doctor didn't choose to perform a chest X-ray probably indicates that the person didn't come in with a deep cough or some other symptom that suggested tuberculosis or pneumonia, and therefore the test wasn't performed. So the observation or lack thereof of a chest X-ray, the fact that a chest X-ray doesn't exist in my patient's record, is probably an indication that the patient didn't have tuberculosis or pneumonia. So these are not independent. So in that model, we do not have the missing at random assumption holding, because the observability pattern tells me something about the disease, which is the unobserved variable that I care about. On the other hand, if I have in my medical record things like the primary complaint that the patient came in, for example, a broken leg, then at that point, given that the primary complaint was a broken leg, I already know that the patient likely didn't have tuberculosis or pneumonia. And therefore, given that observed variable, which is the primary complaint, the observability pattern no longer gives me any information about the variables that I didn't observe. And so that is the difference between a scenario that is missing at random and a scenario that isn't missing at random. For the purposes of our discussion, we're going to make the missing at random assumption from here on. What's the next complication with the case of incomplete data? It turns out that the likelihood can have multiple global maxima. So intuitively, that's almost obvious. Because if you have a hidden variable that has two values, 0 and 1, the values 0 and 1 don't mean anything. We could rename them 1 and 0 and just invert everything, and it would basically give us an exactly equivalent model to the one with 0, 1, because the names don't mean anything. And so that immediately means that I have a reflection of my likelihood function that occurs when I rename the variables. And it turns out that this is not something that happens just in this case. When I have multiple hidden variables, the problem only becomes worse because the number of global maxima becomes exponentially large in the number of hidden variables. And so now we have a function with exponentially many reflections of itself. And it turns out that this can also occur when you have missing data, not just with hidden variables. So even if all I have are things like the difference between, for the purposes of our discussion, we're going to make the missing at random assumption from here on. What's the next complication with the case of incomplete data? It turns out that the likelihood can have multiple global maxima. So intuitively, that's almost obvious, because if you have a hidden variable that has two values, 0 and 1, the values 0 and 1 don't mean anything. We could rename them 1 and 0 and just invert everything, and it would basically give us an exactly equivalent model to the one with 0, 1, because the names don't mean anything. And so that immediately means that I have a reflection of my likelihood function that occurs when I rename the variables. And it turns out that this is not something that happens just in this case. When I have multiple hidden variables, the problem only becomes worse because the number of global maxima becomes exponentially large in the number of hidden variables. And so now we have a function with exponentially many reflections of itself. And it turns out that this can also occur when you have missing data, not just with hidden variables. So even if all I have are data where only some occurrences of a variable are missing its values, even that can give me multiple local and global maxima. So to understand that a little bit in more depth, let's go back to the comparisons between the likelihood in the complete data case and the likelihood in the incomplete data case. So here is a simple model where I have two variables, x and y, with x being a parent of y, and I have three instances. And if we just go ahead and write down the complete data likelihood, it turns out to have the following beautiful form, which we've already seen before, where we have the product of probabilities for the three instances, and each of these can be, well, we've omitted writing the parameters for clarity, and that's going to be equal to, here is the probability for theta x 0, y 0, given the parameters, the second instance, and the third instance. And the point is, this ends up being a nice decomposable function of the parameters, as in terms of a product, which when we take the log ends up being a sum. So the likelihood decomposes, it decomposes by variables, and it decomposes within the CPD. What about the incomplete data case? Let's make our life a little bit more complicated. And whereas before we had these complete instances, now notice that both of these instances have an incomplete observation regarding the variable x. And now let's write down the likelihood function in this case. Well, the likelihood function is now the probability of y0, which is the first data instance, times the probability of x0, y1, which is the second data instance, times another probability of y0. So since p of y0 appears twice, we've squared this term over here. And the probability of y0 is the sum over x of the probability of x comma y0. That is, we have to consider both possible ways of completing the data, x for the different values of x, x0 and x1. And so if we unravel this expression inside the parentheses, it ends up looking like this. Theta x0 times theta y0 x0 plus theta x1 theta y0 given x1. And the important observation about this expression is that it is not a product of parameters in the model, which means we cannot take its log and have it decompose over parameters as a summation, because a log of a summation doesn't decompose. And so that means that our nice decomposition properties of the likelihood function have disappeared in the case of incomplete data. It does not decompose by variables. Notice that we have a theta for the x variable sitting in the same expression as an entry from the P of y given x CPD. It does not decompose within CPDs, and even computing this likelihood function actually requires that we do a sum product computation. So it requires effectively a form of probabilistic inference. So what does that imply, both of these properties that we talked about in the previous slides, what does that imply about the likelihood function? Before, our likelihood function had the form of these gray lines over here. So for example, like this. This is a likelihood function of a complete data scenario. When we have a case of incomplete data, we're effectively summing up the probability of all possible completions of the unobserved variables. And so the overall likelihood function ends up being a product of, ends up being a summation of likelihood functions that correspond to the different ways that I had to complete the data. So this ends up being where this is one such summation. So the likelihood function ends up being a sum of these nice concave likelihood functions, well, log concave likelihood functions. But the point is, when you add them all up, it doesn't look so nice at all. It ends up having multiple modes and is very much harder to deal with. The second problem that we have, in addition to multimodality, is the fact that the parameters start being correlated with each other. So if you remember, when we were doing the case of complete data, we had the likelihood function being composed as a product of little likelihoods for the different parameters. What happens when we have an incomplete data scenario? So when you look at this, you can see, for example, that when x is not observed, you have an active V structure that goes from theta yx through y all the way to theta x. And so intuitively, that suggests to us that there is a correlation, an interaction between the values that I choose for theta y given x and for theta x. And when you think about the intuition for that, it makes perfect sense, because, for example, if theta x chooses to make x0 very, very likely, then most of the instances where x is unobserved will be assigned to the x0 case, and that's going to basically have me assign the data instances to the x0, and that's going to change the estimates of theta y given x0 relative to theta y given x1, because most of the instances now correspond to x0 rather than x1. So that's a correlation between them, and to see that correlation manifesting, let's look at some graphs. And so what we're seeing here is actually the correlation between two entries in the CPD theta y given x. So over here we see theta y given x0, and here is theta 1 given x1. What you see here is the contour plot of the likelihood function. It has 8 data points and 0 missing measurements. And you can see that this is a nice product likelihood function with a nice peak in the middle, and there's no interaction between the two parameters. But as we start to gain more and more missing measurements, you can see that the curves start, the contour plots start to deform. And even with 3 missing measurements, you can see that there is significant interaction between the value that I end up picking for theta y given x1 and the value that I end up for theta y1 given x0. So to summarize, incomplete data is actually something that arises very often in practice, and it raises multiple challenges and issues. How are the missing values generated? What makes them missing turns out to be very important. The fact that there's certain components of the model that are just unidentifiable because there's several equally good solutions. So if you pick the best one, you better realize that there's others that are equally good out there. And finally, the complexity of the likelihood function is another significant complication when doing this kind of, when trying to deal with incomplete data.
we talked about the problem of learning models with missing variables, missing data, and discussed some of the complexities of that learning problem. So now we're going to basically bite the bullet and try and understand how one might go about doing, say, parameter estimation in the context of missing data nevertheless. So let's remind ourselves of one of the more important difficulties in learning parameters with missing data. So let's draw here the likelihood function that we might have. So the x-axis here is the parameter, is a pictorial description of the parameter vector theta, and it's a one-dimensional depiction, but usually, of course, it'll be multidimensional. What we see here on the y-axis is the likelihood function. In the context of complete data, as we might remember, the likelihood function had this really nice form. It was a nice log concave function, and in the context of Bayesian networks, it could actually be optimized in closed form using a simple formula. In the context of missing data, however, the situation became considerably more complicated, and the likelihood function looks more like this. It's this nasty, complicated, multimodal function, which is really impossible to optimize in closed form. So how do we go about optimizing a function that looks like this? It turns out, two general classes of strategies. The first is to use a generic optimization method, such as gradient ascent. So here, for example, we have a pictorial depiction of gradient ascent. We might start out with a particular point in the parameter space, and we compute the gradient at that point, and we go in the direction of steepest ascent, which might take us to the next point, at which point we compute the gradient, and we continue until we reach what is going to be generally a local optimum of the function that we're trying to optimize. Now, what I described right now is a very simple gradient ascent over parameter space, but in general, there's more efficient methods for improving the convergence, the rate of convergence of these algorithms, methods such as line search or conjugate gradient methods that basically are going to get us faster to whatever global optimum, whatever local optimum we're going to end up at. So a key question when applying gradient ascent to functions such as this is how difficult it is to compute the gradient in this high-dimensional space. Fortunately, in the context of Bayesian networks, we can actually come up with a closed-form solution for that gradient, and that solution takes the following form. So the gradient of our log likelihood function relative to a particular parameter, theta of xi given ui. So this is in the context of a standard, say, multinomial Bayesian network, and little xi is a particular assignment to big xy, and little ui is some assignment to its parents. That gradient has the following form. It's 1 over the value of the parameter at the point at which we're computing the gradient times a summation over data instances, m, of the probability of that particular assignment xi and ui to the node and its parents, that particular joint assignment, given all of the evidence in the mth instance at the current value of the parameter. So we basically look at each and every one of the data instances, compute the probability of this event, xi, ui, given whatever observations I happen to have seen, whether xi and ui are observed or not, and then I compute that probability, add this all up, and divide by the value of the parameter. So that's a nice sort of usable formula, except that we have to understand some of the repercussions of that. Specifically, this requires that we compute this probability over a node and its parents, that is a family, given the data m, and we need to compute that for all variables I and for all data instances m. So this effectively means that we have to run inference for every instance, and furthermore, we need to compute the probability for every family in the Bayesian network. Now, fortunately, fortunately, we can at least reduce the second part of this computational cost, which is the fact that we need to run this for all I, by remembering the fact that if we say calibrate a clique tree or even a cluster graph, then when we're done with the calibration, because of the family preservation property, a node and its parents are all going to be in the same clique or in the same cluster. So a single calibration process is going to give us all of these probabilities at once. But that's only true for a given data instance M, which means that effectively what we end up with is the following computational cost, which is that we need to run inference for each and every data instance at every iteration of the gradient process, which is a very costly computation. Now, what are the pros of gradient ascent as an optimization algorithm? It's a very flexible strategy. So whereas we just showed how the formula applies to table CPDs, it can also be extended to non-table CPDs via the chain rule for derivatives, which is not the same as the chain rule for Bayesian networks. However, it also has some significant cons. First, it turns out to be a little bit tricky, not horrible, but a little bit tricky to ensure that the parameters define legal CPDs. So this gives rise to a constrained optimization problem where we need to make sure that the entries in the CPD are all greater than or equal to 0 and sum to 1, and that imposes some additional burden on the optimization problem. And then it turns out that if you want to get any kind of reasonable convergence, you can't just do straight gradient ascent. One needs to do something more clever, like a conjugate gradient or a line search, which again tends to increase the computational cost. The second strategy that one typically uses for optimizing the likelihood function is a strategy that is specifically geared for likelihood functions. So it's a special purpose algorithm that doesn't optimize any old function, but rather just specifically for likelihood functions. What's the intuition behind this algorithm called expectation maximization, or EM for short? The intuition is that really we have a chicken and an egg problem here. If we had complete data, then parameter estimation would be easy because we know how to do maximum likelihood parameter estimation in Bayesian networks. In fact, it's a closed form problem. Conversely, if we had the full set of parameters, then computing the probability of the missing data would also be easy. Easy in the sense that it requires, that it can be done using straight probabilistic inference, which may or may not be computationally easy, but conceptually, computing the probability of the missing data is an easy, well-defined problem. So we have two sets of things that we need to infer or estimate. One is the parameters, and the other is the values of the missing variables, missing data. And each of those is easy given the other. And so what the EM algorithm does is effectively an iteration process, or in fact, one can formally show a coordinate ascent process, where we start out with some set of parameters, use that to estimate the values of the missing data, and then use that completion to re-estimate the parameters, and so on and so forth, until we reach convergence. So more formally, we pick some starting point for the parameters. In fact, one can also initialize on the values of the missing data. It's more standard in many applications to initialize with the parameters, but both are completely legitimate. So say we pick a starting point for the parameters, and then we iterate these two steps. The first is what's called the E step. E step stands for expectation, in which we complete the data using the current parameters. And the second is the M step, standing for maximization, and that estimates the parameters relative to data completion, and maximization comes from basically something like maximum likelihood. That's where the M in maximization comes from. And it turns out that this iterative process is guaranteed to improve the likelihood function at each iteration. That is, at each iteration, the likelihood function is going to be better than it was before the previous one. And so this process is an iterative improvement process. Let's make this process more precise. So let's consider each of those E step and M steps separately. So the expectation, or E step, remember this is going from the parameters to the missing variables. For each data case D and each family, X comma U, we are going to compute the probability of X comma U given the observed values in that data instance, and given the current parameter setting theta t. With that completion, which note is a soft completion, because it's a probability distribution over the parameters, over the missing variables, not a single assignment to X and U. With that soft completion, we're going to compute what is called the expected sufficient statistics. The expected sufficient statistics is very similar to the sufficient statistics that we had before. When we were computing sufficient statistics, we were counting the number of times that we saw a particular combination X comma U. Remember, we had M of X comma U as being our sufficient statistics. Now we have a soft completion, and so we have expected or soft sufficient statistics, which we're going to denote with an M hat, subscripted by the parameter vector that gave rise to the completion. And M hat sub theta t for a particular assignment X comma U is going to be simply the sum over all of the data instances of the probability that we just computed, the probability of X comma U given the assignment D sub M and the parameters theta t. And that is a notion of expected counts or expected sufficient statistics, which we're now, in the context of the M step, going to use as if they were real sufficient statistics. And so we're going to take these expected sufficient statistics and use them to perform maximum likelihood estimation using the exact same formula that we would have used had these been real sufficient statistics. So specifically, for example, in the context of multinomial Bayesian networks, we would have that the next value of the parameters theta t plus 1 given xu is m bar of theta t xu divided by m bar theta t of u, which is, in using these soft counts, the fraction of xu's among the u's. Let's consider a concrete, very simple example, which is that of Bayesian clustering. So what we see here is your standard naive Bayes model, where we have a single class variable and a bunch of observed features. And the assumption here is that the class variable is missing. That is, it's sometimes or never, in most cases, never observed in the data. And so effectively, we're trying to identify what are the categories or classes of instances in this data under the assumption that within each class, the feature values are independent. That is, the features are conditionally independent given the class, as in the naive Bayes model. So instantiating our formula from the EM algorithm for this setting, we get the following very natural formula. So the sufficient statistics for the class variable is simply the sum over all of the data instances of the probability of the class variable given the observed features for that data instance, and the and the current value of the parameters. That is, it's the soft counts of how many instances fall into each category when each instance is allowed to divide itself up across multiple categories, so to use a soft assignment. The second set of sufficient statistics, which represent the dependency between one of the features and the class variable, is m hat sub theta of xi, say, comma c, and that once again sums up over all the data instances and simply looks at the probability of a particular class variable and a particular feature given the observed instances, the observed features at that particular instance. Now, with these expected counts, we can now go ahead and do maximum likelihood estimation, and that gives rise to the following very simple equations, which is that the theta c is equal to m hat sub theta of c divided by m, which is the total number of data instances, and theta of little xi given c is going to be assigned m hat theta xi comma c divided by m hat theta of c, which again is the standard formula, but using soft rather than hard counts. So to summarize the EM algorithm, we have, in this case, the exact same problem that we had in the context of the gradient ascent algorithm, which is that we need to run inference, the probability of xi comma c, for each data instance at each iteration. As for the gradient ascent algorithm, this only requires a single calibration because of the same family preservation property that was useful there. It applies equally here. What are the pros of the EM algorithm? It's very easy to implement on top of an existing maximum likelihood estimation procedure that one might have for complete data. So having implemented an MLE procedure, one can easily build on top of that by adding a separate E-step for computing the expected sufficient statistics. Empirically, it turns out that the EM also makes very rapid progress in terms of converging to a better and better set of parameters, especially in early iterations. And we'll see some empirical results for that in a bit. The cons of the EM algorithm is that the convergence generally slows down at later iterations, and so it requires sometimes that later iterations might use, say, some kind of conjugate gradient algorithm because it turns out that that's more effective there. We previously defined the EM, or expectation maximization algorithm, which, as it happens, is one of the algorithms that's most commonly used in practice because of its simplicity and because it's so effective in dealing with missing variables, missing values. But we didn't give much justification for why the algorithm works. So what we're going to do now is we're going to give at least a little bit of theoretical intuition as to how the formulas that we are using in the EM algorithm are arrived at. So let's start with providing a little bit of a more formal intuition. So in some sense, EM is also, like gradient ascent, a local search procedure. But unlike gradient ascent, it uses a less local approximation to the likelihood function. So specifically, if this is our likelihood function, as we had before, or rather the log likelihood, really, in practice, what we're going to do is we're going to approximate the we're going to take the current point that we're at, because remember, this is a local iterative search. We're going to take that point and we're going to approximate the function at that point using this blue line over here. Now, gradient ascent approximated the function at this point using a straight line, a linear approximation. EM approximates the function at this point using this nice curvy function, which, as it turns out, is, as we'll see, a log likelihood itself. It's in fact the log likelihood with complete data. And having constructed this approximation, it now jumps to the maximum of this function, which, because this is a log likelihood with complete data, can be maximized in closed form using maximum likelihood estimation. So this is the intuition behind DM. Let's see if we can formalize that a little bit. So first, some notation. D is the observed data in a given instance, and we're going to do one instance for the moment. H is the hidden variables in that instance, and we're going to assume that somehow from somewhere we have a distribution over the values of the hidden variables within that instance. So there's no distribution over the value. I mean, we're not going to impose a distribution over D. D is observed, but for the hidden variables, we have some kind of distribution over the values that they might take. So now let's remind ourselves what the log likelihood function looks like when we have complete data. So the log likelihood function for the parameters theta, given now a pair D comma H, where H is an assignment to big H, to the hidden variables, is simply by the definition of the log likelihood and the decomposition of the likelihood over the chain rule for Bayesian networks. It's a sum over the variables in the network, the sum over all possible assignments to a node and its parents of an indicator function that says in this particular a pair, D comma H, do the variables xi and ui take on this particular values little xi and little ui? And if so, we're going to multiply in the log of the parameter corresponding to that entry in the CPD. Now, this is a really complicated way, you might think, to write what is effectively a sum of the log of theta of a node given its parents in the assignment D comma H, but there's a reason why we're going to write it this way, and which will become clear in a moment. So now let's imagine that what we have is the distribution over Q, the distribution Q over H, and now we're going to look at the expectation of this log likelihood function relative to the distribution over H. So now rather than H being given, we have a distribution over H, and we're going to look at the average or expectation of the log likelihood relative to the distribution Q sub H. Now, importantly, because of the linearity of expectation, that expectation is going to push its way past the first summation, the sum over I, past the second summation, which is the sum over assignments little xi and little ui, and we're going to end up with the following equation, which is the expectation relative to Q of this indicator function that we had on the previous line. And notice that we can also take log of theta xi given ui out of the expectation because that's fixed relative to h, which is exactly why we wrote the formula in this complicated form. So the one final step of this derivation is now to simplify this expectation over here, the expectation relative to q. And this expectation, when you're taking an expectation of an indicator function, which is simply an event, in this case it's the indicator function of the event xi equals little xi and ui equals little ui, that expectation of an indicator function is simply the probability. So this entire expectation turns out to be equal to the probability of little xi comma little ui under the distribution Q. And so we have now converted this expected log likelihood into this summation that utilizes probabilities relative to the distribution Q. So working forward from this formula, now let's consider the case where we have multiple data instances. So now we have a set of distributions, one for each data instance, and that also depends on the current parameter setting theta t. So now we're in the midst of an EM iteration, and we're going to use the current parameter setting theta t to define the probability distribution over the hidden variables, and that's going to be defined as the probability of the hidden variables given the observed variables and given the current setting of the parameters theta t. we now look at the sum of these expected log likelihoods, so the sum of one for each data. Now let's consider the case where we have multiple data instances. So now we have a set of distributions, one for each data instance, and that also depends on the current parameter setting theta t. So now we're in the midst of an EM iteration, and we're going to use the current parameter setting theta t to define the probability distribution over the hidden variables, and that's going to be defined as the probability of the hidden variables given the observed variables and given the current setting of the parameters theta t. We now look at the sum of these expected log likelihoods, so the sum of, over all of the data instances, little m equals 1 to big M, of the expectation of the hidden variables relative to this distribution that we just defined, qt sub m, of this log likelihood. We can now plug in the equation that we had up here, but substituting for p, the definition of q for what we see here, the p of h given d and theta, and that gives us this equation over here, the sum over I, sum over little xi comma little ui, all possible assignments to the family, sum over the data instances of the probability of xi comma ui given the data instances and the current parameters times the log of the current parameter value. Taking this one step further, specifically looking at this summation over m as a separate entity, we can see that this is really the expected sufficient statistics that we defined in the context of the EM algorithm. And so we now have that that this expected log likelihood function is the sum over I, the sum over little xi ui of the expected sufficient statistics for xi comma ui times the log parameter value. And the important point here is that this is just like a log likelihood function for complete data using the expected sufficient statistics. So the function that we're optimizing is this expected log likelihood, and just a simple mathematical derivation tells us that that is the same as optimizing a log likelihood function using these expected sufficient statistics. And we know exactly what that optimum looks like because it's the same as the standard maximum likelihood estimation problem. And so going back to the diagram that we started out with, the function, this blue function that we're using here as an approximation, is this expected log likelihood. And this optimization that we're doing here basically uses the expected sufficient statistics to do maximum likelihood estimation, which is exactly the M step. So the E step, using these expected sufficient statistics, the sum over little xi ui of the expected sufficient statistics for xi comma ui times the log parameter value. And the important point here is that this is just like a log likelihood function for complete data using the expected sufficient statistics. So the function that we're optimizing is this expected log likelihood, and just a simple mathematical derivation tells tells us that that is the same as optimizing a log likelihood function using these expected sufficient statistics. And we know exactly what that optimum looks like because it's the same as the standard maximum likelihood estimation problem. And so going back to the diagram that we started out with, the function, this blue function that we're using here as an approximation, is this expected log likelihood. And this optimization that we're doing here basically uses the expected sufficient statistics to do maximum likelihood estimation, which is exactly the M step. So the E step constructs this function by computing the expected sufficient statistics, and the M step gives us this maximum from which we now proceed to do the next iteration. Using this kind of intuition, we can actually prove two very important results regarding the expectation maximization algorithm. The first is that the likelihood function, or the log likelihood function, improves at every iteration. That is, the log likelihood at iteration theta t plus 1 is greater than or equal to the log likelihood at iteration theta t, or commensurately for the likelihood. The second result that we could prove is that at convergence, that is, at the point where theta t plus 1 is not changed relative to theta t, then we can be guaranteed that theta t is a stationary point of the likelihood function. What does a stationary point mean? It means a point where the gradient is 0, which in principle can be either a local minimum, a local maximum, or a saddle point. But it's very difficult when you're doing hill climbing to actually land exactly at a local minimum, because that's the only time that we will be converged to local minimum is if a step of EM. So if here is a function, it's very difficult to imagine having an EM step that lands us exactly at this local minimum, because that's the only point at which we won't continue to make progress. And so de facto, when we're doing this kind of climbing and we achieve convergence, it means that we have achieved a local maximum of the likelihood function, which is the same guarantee, unsatisfying as it might be, that we have for gradient descent. We described the expectation maximization algorithm and gave the formulas for how to use it, but we didn't talk about how it might perform in practice. So let's talk about that a little bit. So first, let's look at how EM behaves as a function of the number of iterations. So over here on the x-axis, we see the number of iterations going from 0 to 50. And on the y-axis, we have the log likelihood of the average training instance, so averaged over all of the training instances, which is the objective that the EM algorithm is trying to optimize. Remember, EM is a maximum likelihood optimization algorithm, so what we're showing here is effectively how the objective improves. And so the first observation that we have is that, as we effectively stated as a theorem, so this shows that the theorem is true, the log likelihood increases consistently or monotonically over iterations t. So that's good. So it shows that our theorem is correct. But let's understand what happens now as the algorithm continues to evolve. We see that in the early iterations, so up to about, iteration 8 or 10 in this context, the algorithm, the log likelihood exhibits a very sharp improvement, but then it asymptotes. And so we might think that when we get to iteration 10 or so, right around here maybe, there's no point continuing to run because there's no more increase and we've achieved convergence and we might as well stop. Turns out that's not quite right. What we see here is, for the same model with the same graph, the x-axis is iterations and the y-axis is the value of different parameters in the model. And over here we see the same iteration 10, and we see that although the log likelihood no longer continues to improve after iteration 10, as we can see in the left-hand graph, various parameter values actually exhibit extremely sharp changes after iteration 10. Specifically, the blue parameter goes down significantly, the black parameter goes up significantly. And so we see that convergence in the likelihood space, which is what we have on the left, is not the same as convergence in parameter space. Which means that if we're trying to gauge convergence, we probably ought to look at convergence on parameter space. However, it's also important to realize that carrying EM through to convergence is not necessarily the best idea. So what we see here is the same graph of the training log likelihood per instance, but on the right-hand side, we can see the log likelihood per instance on test instances, that is, instances that the algorithm was not trained on. And what we see is that while the log likelihood of test instances also increases sharply up to about iteration 10, after that it starts to decrease gradually. And so, in fact, as the algorithm is continuing to modify its parameters and slightly improve the training log likelihood, the test log likelihood in this particular case actually goes down. So this is an example of overfitting. In this case, it's numerical overfitting to the specific data instances that we have, or the noise in those data instances. And in order to avoid that, there's two main strategies that people adopt. The first is to use a validation set or cross-validation to determine the time t at which we should stop doing iterations. And so we basically measure log likelihood on a test set and say, okay, at this point we can see that it's starting to go down, and so we should just stop doing iterations. This is potentially a computationally costly procedure, however, because evaluating the test log likelihood means that we need to run inference on the test instances, and that can be expensive. So a cheaper strategy is to use some kind of map assignment rather than maximum likelihood estimation, with the same benefits that we saw when doing estimation for the complete data case. Basically, a prior smooths out the estimates and makes them less susceptible to noise in the training data. So that's one aspect of the behavior of the expectation maximization algorithm. And by the way, the same phenomena will also happen if we use gradient ascent. So this is really orthogonal in many ways to the specifics of the optimization algorithm, except the very sharp increase at the beginning, which is very characteristic of EM. A very different problem that we already mentioned before is the fact that both EM and gradient ascent effectively achieve only a local optimum of the log likelihood function. So what we see over here is, on the x-axis, the number of samples m that we're training on. So this is not iterations anymore. This is the number of samples. And the y-axis is the number of distinct local optima that the algorithm found over 25 iterations. So, sorry, 25 applications of the EM algorithm initialized at different random starting points. So what we see here is we have three lines. The blue line represents 25% missing data. The red line is 50% missing data. So 50% of the entries randomly were omitted. And the black line is when you have a hidden variable. So in this case, the fraction of missing data is actually not perhaps as large, but there is one variable that we never get to observe in any of the instances. And what we see in both the blue line for the 25% and the red line for the 50% is that initially we have a very large number of local optima. In fact, initially pretty much every iteration of EM finds a distinct local optima. But then as we have more and more training instances, the algorithm begins to be able to better identify a global, a smaller number of optima come to the forefront, the other ones kind of become less dominant or disappear. Now, the more missing data we have, so in the red line, the slower this process to reduce the number of local optima. And when we have hidden variables, which is this black line over here, the local optima never go away. Now, you might say that, fine, we have local optima, but maybe we don't care. Maybe these local optima are all about the same and doesn't really matter which one we land at. Unfortunately, that doesn't turn out to be the case. So here we have on the x-axis, sorry, on the y-axis rather, a particular log likelihood value that might be achieved on the training set by a run of expectation maximization. And on the y-axis, we have the percent of runs that achieve a particular log likelihood value. And we can see that there are a huge variation in the log likelihood values that are achieved by different runs of the expectation maximization algorithm. Which brings us to the point that initialization is absolutely critical to the performance of an algorithm such as expectation maximization. And there's different strategies that people adopt in order to try and get to a better local optimum. So first, and perhaps easiest to implement in some sense, is the use of multiple random restarts. So we randomly sample parameters, for example, and we initialize EM at these different points, and we run EM to convergence, and then we pick the run of EM that has the highest training log likelihood, which after all is the objective that we're trying to optimize. In some cases, we might have some amount of prior knowledge that we might use to initialize the algorithm. For example, we can have some prior knowledge about the parameters, or if we're initializing on the E step, we might have some prior knowledge about the assignment, say, of variables to cluster, of instances to clusters, for example, from some other source, maybe demographic data for people or something like that. And finally, a common and quite effective initialization strategy is to use a simpler algorithm rather than full-scale EM, because it turns out that while EM is very powerful, that also makes it more susceptible to getting stuck in certain local optima, whereas some simpler algorithms, for example, in the context of hidden variables, we might use a simpler clustering algorithm that you might have heard about in a different context, k-means, or hierarchical agglomerative clustering, which is a simpler algorithm, not as powerful, but is also somewhat less susceptible to local optima. And so we might initialize from that and then run EM to get a better output than these simple algorithms might give rise to. So to summarize, we've seen that convergence of the likelihood function is not the same as convergence of the parameters, and so we have to decide which one we actually care about. We've also seen that running the algorithm to convergence, all the way to convergence, can lead to numerical overfitting. We talked about strategies to get to avoid this problem. We talked about local optima and the fact that they're unavoidable. And furthermore, they increase with the amount of missing data. So the more missing data we have, the more local optima we have. And furthermore, they decrease with the total amount of data, but not if we have hidden variables, at which point you're stuck with them no matter how much data you have. We also showed that local optima are not a fake problem. That is, which local optimum you land in can actually be a significant factor in terms of the performance that the algorithm achieves in terms of log likelihood. And therefore, smart initialization turns out to be often critical for the performance of algorithms that learn with latent variables and with missing data. Perhaps the most common use of the expectation maximization algorithm is to the problem of learning with latent variables. These are situations where there's a certain set of variables that we just never get to observe, but they turn out to be important for capturing some important latent structure in the distribution of the data instances that we have. So let's look at a number of these examples and talk about how EM was applied in those settings. So perhaps the simplest example is in the context of Bayesian clustering, where we have some kind of latent class variable and some set of observed features. And we're trying to basically segment the instances that we have into categories where we assume that for each category there's a similar distribution over the observed features. And specifically in many of these applications, that distribution takes the form of a naive Bayes model. That is, that the features are independent once we're given the class. So one example application of this is to segmenting a set of users into similarity groups. And so one cute example of that is the following segmentation of users on the MSNBC website based on which of the stories on the MSNBC site the users chose to click. And this is due to Jack Breeze and colleagues at Microsoft Research. So here we're going to see 4 clusters. The first of these is a cluster that a human given name to, because the machine doesn't give a name to the cluster, it just calls it cluster 1, turns out to be readers of commerce and technology stories. So these are people for whom the highest probability clicks on stories were, for example, email delivery isn't exactly guaranteed, or should you buy a DVD player. So remember, the stories are the features and they're binary variables. Did you click or did you not click on that particular article? And the cluster is the segmentation of the users into these different categories. So this is category 1. The second cluster are people who primarily clicked on sports stories. So the highest probability features in for this user group were, for example, stories such as Cowboys are reborn in win over Eagles or something like that. The third cluster are the people who went to the top page and basically clicked on the top promoted stories. This says 29% of the users, and one can date this by at least this article, although this one seems pretty perennial. And so we can so that's a third category. The last one was the surprising one. These are people who traversed all over the site. So for the previous 3 categories, there were actual pages that existed for sports, for top promoted stories, and for commerce and technology. This last category are people who went all over the site to look for stories that you might call softer news. And so this was an interesting discovery for the MSNBC website about its user population, and suggested that the website might be better redesigned to capture this kind of structure and give these users a page where they can find these articles. A very different application is to speech recognition, which is one that we've talked about before. In the context of speech recognition, we've already discussed that the standard representation of choice is a hidden Markov model. And in a hidden Markov model, we have hidden variables and we have parameters. The parameters are the parameters of the HMM, the transition probabilities, for example, between one phone and the other, or the acoustics, or the probability over the acoustic signal that we observe for different pieces or states within a phone. The latent variables are the segmentation of the initial acoustic signal into which state it belongs to, that is, which phoneme and which part of which phoneme. Those are the hidden variables. And that's an awful lot of hidden variables, because if we're just given an undifferentiated, unsegmented signal, it's very difficult to assign as a piece, a small slice of that segment of that speech into one phoneme versus the other. So in order to train well a speech recognition HMM, the standard strategy is a bottom-up bootstrap training, where one first trains the phone HMM separately for each phone using a phone database. Now this too is done using EM, because the breakdown within a phone into these little constituent pieces is not labeled, and so it still requires that we do EM to address the issue of latent variables. But at least it's now self-contained, because you're only training a model for a single phone, like P. With that model trained, we can now one can now take entire words and use the model initialized with the phone with the model trained on individual phones to now train the higher level model, and one still retrains the phone HMM parameters in the context of this larger training regime where one now trains on entire words, but the fact that one seeded the model with this much more correct initialization on the parameters allows the segmentation in the E step to be performed moderately correctly and gives rise to a much better local optimum in the speech recognition problem. A yet different application is that of 3D robot mapping. So this is an application that's due to Thrun et al. And here the input to the problem is a sequence of point clouds obtained by a laser rangefinder that were collected by a moving robot. And the target output is a 3D map of the environment as a set of planes. And you'll see the difference as to why we want the planar map when we look at the demo. Here, the parameters of the model are the location and the angles of the walls or the planes in the environment. So we have no idea a priori where their walls and how they're situated. The latent variables are an association variables, which assign points to walls. And so the EM algorithm effectively in the E step figures out which points go with which wall, and in the M step it figures out how to move the wall around to better fit the points that were assigned to it. So what we see here is the raw data collected by the robot. The red box is the robot moving around in its environment. The red beams that emanate from the robot are the directions that the laser took in order to collect the point cloud. And what we see here is the point cloud that was collected by the robot as it traversed the environment. And even just looking at this image, we can already see that there's a lot of noise in the laser range data, and that this is going to give rise, as we can see, to a very noisy map of the environment. If we now look at the model constructed by EM, so now we're going to see the planar map constructed by the robot, and this is done on the fly actually as the robot is moving, we can see that walls are constructed when there is enough data to support them, and that's when enough points are assigned to a wall, then that wall gets constructed and its pose in the environment gets determined by the EM algorithm. And so we can see that this constructs a much more plausible and realistic map of the environment than just looking at the raw point cloud data. A yet different application is also in the context of 3D laser range scans, and we picked those not because these are the most common applications of EM, but because they give rise to some pretty cool movies. So here is the problem of getting, in this case, 3D range scans of a person in different poses. And the goal is to see whether by collecting a bunch of these poses, one can reconstruct a 3D skeleton of the person. So from the front and from the back. So in this particular case, the first problem is actually to correspond points in the different scans to each other. And in this case, that was done by a different algorithm that I'm not going to talk about now, although it also used graphical models. In fact, it used a belief propagation algorithm. But now let's talk about the clustering problem, that is the problem of assigning points in each of those scans to body parts. So here we have the notion of a cluster, which in this case corresponds to a part. And each part in a given scan of the person has a transformation. So that's why we have a plate around each of the parts, because we have an for each of those parts there is multiple instantiations in the multiple scans that we have of the same person in different poses. Now, a landmark is a particular point on that person in that part. And if we knew the part, that is, if we had the part assignment, which is a latent, unobserved variable, then we could predict how the point that we see on this scan would translate to the point on this scan, because that would be effectively a deterministic or close to deterministic function of the unobserved transformation of the part, that is the fact that the arm, say, moved from this pose over here to this raised arm pose over here. So given the transformation, and given that we know which part the point or landmark is assigned to, we can predict how the point transformed from its original position to its new position. So this is a way of clustering points into parts, and one can run EM on that, and if one does that, effectively one gets pretty much garbage, because it turns out that there is enough muscle deformation to make the actual positions here fairly noisy, and it's very difficult to get correct part assignments from that. But if we now add an additional component into this model, specifically contiguity of space, we can now consider, say, two points that are adjacent to each other and impose the soft constraint, not the hard constraint, but a soft constraint, that a part assignment of 2 points that are adjacent should be softly the same. It doesn't have to be exactly the same, because otherwise, of course, everything would be assigned to the same part, but it's a soft constraint, which is actually an MRF constraint. In fact, it's even an MRF constraint which is associative or regular, as we discussed before. And so this model now that actually does the clustering not of each point in isolation, but rather assigns points jointly to parts, taking into consideration the geometry of the person's body, is a considerably better gives rise to considerably better outputs. And what we see here is the EM algorithm in action. And we can see that the algorithm converges very nicely to a partition of the points into different parts. And from this one can easily reconstruct the skeleton. A final application that uses EM in yet a different model is one that was used in this helicopter demo alignment. Here the input, this is work that was done at Stanford by Andrew Ng's group, and here the input to the algorithm is basically different trajectories of the same aerobatic maneuver flown by different pilots. So they were all trying to do the same thing, but each person has their own idiosyncratic way of doing this, and so the exact sequence wasn't, as we'll see, exactly the same. The goal of this was to produce an output which aligns the trajectories to each other, and at the same time learns a probabilistic model of what the target or template trajectory ought to have been. So how does this get represented as a graphical model? Here we have a latent trajectory, which is the intended trajectory that the users were aiming for, and the states in those are labeled as z's, and we have parameters that tell us how one would move from z0 to z1 and so on. So those are the model parameters of this Markov model, although it's a hidden Markov model, as we'll see. The expert demonstrations, that is what we saw in terms of what the expert did at each point in time, is a noisy observation of the intended trajectory. But we don't actually know which point in the trajectory the expert observation comes from. And so we have this additional set of latent variables, which are the time indices, and they basically tell us that at time tau 0, the demonstration, which of the true states in the intended trajectory the expert was at this point. And tau 1 tells us which point in the intended trajectory the expert was in time 1, and similarly for time 2, and so on, where k is the expert demonstration. So k is the index on the experts. So this problem can be solved using an expectation maximization algorithm where we have two sets of latent variables, the taus and the z's, and one set of model parameters, which are the transition probabilities, although it's possible that it's also possible to learn the model for the expert demonstrations, or we could simply fix the noise model. Both are legitimate strategies. So let's see how this works. Let's first look at the original trajectories, and we can see that initially they start out aligned, but after a while they start to diverge. So for example, by the time we're right about here, you can see that the different experts are very different places in the trajectory. And so the question is, how can we address that limitation? And so if we look at the aligned model, which is what we see over here on the right, we can see that the algorithm manages to maintain alignment fairly well, and that here you can see that the different trajectories are pretty much at exactly the same point in the sequence. And from that, it's much easier now to learn the model and have the helicopter fly the correct trajectory. So one important issue regarding latent variables is the number of values of the latent variables, and this is something that has been implicit in many of the applications that I've mentioned in this module. So how many user clusters do we have, or how many different pieces of a phone are there? And so how do we pick that cardinality for the latent variable? If we use likelihood to evaluate a model with fewer values for the latent variable versus one with more, it's in the same way that likelihood always overfits, we will find that more values is always better because it's a strictly more expressive model and can therefore achieve a higher likelihood. Now, one can circumvent that in the same way that we circumvented the likelihood overfitting phenomenon in the context of other structure learning algorithms. So we can use, for example, a score that penalizes complexity, such as the BIC score. As we mentioned back then, the BIC score tends to underfit, and so there has been a range of extensions to the Bayesian score for the context of incomplete data. These are always approximations because we can't actually do the integration required for the Bayesian score for incomplete data. And so we have approximations to the Bayesian score that turn out to work much better in practice than BIC in many practical applications. There's also other strategies that people have adopted. For example, we can use metrics of cluster coherence to look at a cluster and say, ooh, it seems like this cluster is really incoherent, so maybe there's really two clusters in there, so maybe we should split it up. Or these two clusters are very similar to each other, maybe we should merge them. And there's various heuristic exploration algorithms that basically split clusters and add clusters in a way that hopefully converges to the right number of clusters. And finally, of great popularity in the last few years is a range of methods that are based on Bayesian techniques. These are methods, often the most commonly used class is called Dirichlet processes, which instead of picking a single cardinality for the latent variable, basically maintain a distribution over the cardinality. And then instead of picking a single value for that cardinality average over the different cardinalities using often techniques such as Markov chain Monte Carlo, although there's also other approaches. But this turns out often, the problem of picking latent variable cardinality is often one of the trickier issues that one has to deal with when learning with latent variables. To summarize, latent variables are a really common scenario in the context of learning graphical models and one of perhaps the most common setting for incomplete data. And it turns out that when we want to construct models for richly structured domains, the introduction of these latent variables can be critical in the success of the model. We've already mentioned that latent variables satisfy the missing at random assumptions, and so the expectation maximization algorithm is applicable in this case and is very commonly used for optimizing latent variable models. However, we've already discussed this previously as well, that when we're learning with latent variables, we have serious problems both with identifiability of the learned model as well as multiple optima that are often even symmetric reflections of each other, which is a facet of unidentifiability, but also ones that are not reflections or just symmetric permutations of each other, and those really necessitate a good initialization strategy. And we mentioned that picking variable cardinality for the latent variables is a key question in these latent variable models, and one to which a lot of work has been devoted, especially in the last few years.